Welcome to The Explainer. So today, we're diving straight into the absolute cutting edge of the global semiconductor industry. And yeah, that pun is absolutely intended. Look, we hear about the AI revolution all the time, right? We talk about the crazy software, the massive data, the mind-blowing outputs. But the giant physical infrastructure that actually makes all of this possible, it's usually completely hidden from view. So today, we're going to explore a massive bottleneck in that very infrastructure, and honestly, it's absolutely fascinating. I mean, think about it for a second. What on earth connects the world's most advanced artificial intelligence to a humble industrial grindstone from 1937? It sounds like an impossible riddle. We usually picture high-tech AI as something born purely out of sleek computer code, sterile labs, and Silicon Valley startups. But we're going to uncover a massive historical mystery behind the actual physical brains of AI. Let's solve this puzzle together. Okay, let's dive into this. Section 1. The unsung semiconductor hero. You know, we're always hearing about the glamorous side of the business, the so-called front-end giants. We're talking NVIDIA designing the circuits, TSMC manufacturing them, ASML building these incredibly complex lithography machines. These are the trillion-dollar household names making circuits smaller and smaller. But there is this whole hidden half of the manufacturing process that practically never gets the spotlight, even though our entire modern tech world would literally collapse without it. Meet the back-end giant, Disco. This unassuming Tokyo-based company holds a near-global monopoly on the most critical final steps of chip making, cutting and grinding. To put this in perspective, try to wrap your head around this number. 150 trillion yen. That is the projected size of the global semiconductor industry by the year 2030. And it's largely being driven by the sudden, explosive growth of generative AI. It's just a staggering amount of money. And the craziest part? Almost every single advanced chip fueling that massive industry has to eventually pass through Disco's machines. Because here's the harsh reality check of chip manufacturing. You can have a 30-centimeter silicon wafer printed with the most advanced 2-nanometer circuits on the planet, representing billions of dollars in R&D, but those wafers are completely useless until they're cut. If you can't safely slice that single, incredibly delicate disc into thousands of individual functioning chips without destroying them, well, that multi-billion-dollar wafer is basically just a very expensive coaster. Moving on to Section 2, why AI needs thinning. For the longest time, the whole tech industry was just obsessed with making circuits smaller and smaller on a flat 2D plane. But with the rise of AI, just shrinking circuits, it isn't enough to get the massive performance leap we need anymore. Generative AI requires processing unimaginably huge amounts of data at lightning speeds, and flat chips just aren't cutting it. Enter HBM, or high bandwidth memory. This basically involves stacking multiple memory chips vertically. So instead of spreading chips out flat next to an NVIDIA processor, manufacturers are now literally building them up like little microscopic skyscrapers to boost data transfer speeds and overall performance. And this requires a completely new playbook. Step 1, you manufacture smaller, individual pieces called chiplets. Step 2, you grind them down until they are practically paper thin. Step 3, you stack them 8, 12, or even 16 layers high. But obviously you can't just stack standard thick chips on top of each other, right? The final component would be way too bulky to fit inside modern servers and phones. They absolutely have to be made unimaginably thin first. Okay, let's put some real scale to this challenge. When a newly minted silicon wafer first comes off the production line, fully loaded with those intricate printed circuits, it starts out at roughly 0.8 millimeters thick. It's rigid, and honestly, relatively thick in the grand scheme of things. Now, what's really interesting about this next part is the target thickness. Get this, 0.05 millimeters. We're talking 50 micrometers. That is quite literally thinner than a single strand of human hair. Disco's backend machines have to take that rigid 0.8 millimeter piece of silicon and grind it down to a microscopic, highly fragile, hair-thin sheet just so they can be stacked together. All right, Section 3, 3 walls of precision. Taking a super brittle silicon wafer, getting it down to hair-like thinness, and then cutting it into thousands of tiny squares is, well, it's like trying to solve an impossible physical puzzle. Competitors are constantly trying to break into this market, but they continually fail because they slam face first into 3 massive technical hurdles. These hurdles act as an almost unbreakable moat around Disco's global monopoly: the blade wall, the stopping and control wall, and finally, the thinness wall. Let's actually break these down so you can see exactly what kind of extreme engineering we're dealing with here. First up, we have wall number 1, the blade wall. We are talking about circular dicing blades that are literally only 20 to 30 micrometers thick. Again, thinner than a human hair. And what makes Disco so wildly unique is that they don't just build the heavy cutting machinery, they actually custom make these microscopic blades themselves. They precisely embed them with microscopic diamond grit, and they can tweak the density and hardness depending on whether they're cutting standard silicon or newer, even harder materials. Then we hit the second wall, the control wall. 30,000 RPM. That is the extreme speed at which these delicate, paper-thin blades spin. Just imagine for a second spinning a blade thinner than a hair at 30,000 revolutions per minute, all while constantly pouring water over it to keep it cool. That blade absolutely cannot vibrate, it can't wobble, it can't deviate even a fraction of a hair, or it will just instantly destroy the circuitry it's supposed to be cutting. So the crucial point here is that the machine has to perfectly navigate a tiny 10 micrometer cutting path. It's essentially a microscopic alleyway running exactly between the printed circuits. It has to slice straight through that microscopic lane without chipping any of the surrounding circuits, and it has to stop at the absolute perfect microdepth without cutting too deeply into the base tape. It's just absolute, flawless micro-precision. And finally, we reach wall number 3, the thinness wall. When you use a grinder to thin a silicon wafer down to 50 micrometers, it becomes incredibly fragile, almost like a super thin layer of glass. The grinding process has to leave a mirror-smooth perfection on the back of the chip, because if there is even one invisible microscopic scratch or even just a single particle of dust left on that 30-centimeter disc, the stress will cause the entire wafer to instantly shatter. The air purity, the water temperature, the pressure, literally everything must be flawless. Section 4. 80 years of grinding. Okay, we've talked a lot about cold, hyper-advanced machinery and crazy tight tolerances. But the true secret weapon of Disco isn't just metal and diamond dust. It's actually the humble, deeply human history that built this technology from the ground up. And this perfectly answers our riddle from earlier. See, Disco didn't start as some high-tech electronics company. Back in 1937, they were known as Daiichi Seikosha, operating in Kure, Hiroshima, just making ordinary industrial grindstones. You know, basic abrasive wheels for cutting metal and stone. In the 1960s, as early semiconductors started emerging, they adapted those exact same grindstone principles to cut silicon. Fast forward to the 2020s, and that unbroken 80-year obsession with just grinding and cutting things perfectly has handed them a total monopoly in the generative AI chip market. There's this amazing guiding philosophy behind all of this. The source puts it perfectly. The initial cut relies on the intuition and feel, or candikoro, of the engineers existing entirely outside the manual. No matter how much high-tech automation is packed into modern factories, the true moat protecting Disco is this deeply accumulated human intuition. When a completely new, harder semiconductor material is invented, the old manual is basically useless. It takes the hands-on feel of a veteran engineer to test and know exactly how to adjust the blade, the speed, and the water to nail that perfect first cut. And this brilliantly illustrates their whole, holistic, overarching strategy. They build the machine, they create the custom consumable blades, and they refine the grinding techniques entirely in-house. They don't just sell a factory a machine and then walk away. By controlling the equipment, the blades, and the technique all at the same time, they've created this perfectly tuned ecosystem. It's an 80-year-old feedback loop that competitors just flat out cannot replicate by buying off-the-shelf parts. Bringing it all together in Section 5, the final cut. Let's zoom out for a second and look at the absolute real-world stakes of this single, decidedly unglamorous step in the global tech supply chain. Because it really is the ultimate irony of the tech world. A state-of-the-art front-end semiconductor factory can literally cost trillions of yen to build. You have brilliant engineers spending weeks carefully printing these complex nanometer-scale circuits onto wafers. But all of that immense effort, all of those billions of dollars, relies entirely on Disco's final microscopic cut. If that tiny hair-thin blade wobbles for even a fraction of a second at the very end of the line, the entire multi-billion-dollar wafer is instantly destroyed. Which leaves us with this final, really profound thought to consider. No matter how incredibly smart artificial intelligence becomes, and no matter how much it starts to feel like absolute magic, its physical brain must ultimately be cut, ground, and shaped by 80 years of human history and intuition. The completely invisible physical foundations of our entire digital future are resting on the shoulders of these unsung manufacturing heroes. It really makes you wonder, what other hidden giants are out there quietly running our world from behind the scenes? Thanks so much for joining me on The Explainer today. Keep questioning, keep learning, and I'll catch you next time.